Hi everybody, this is the review for the fourth midterm. It occurs in week 15, the last week of classes before finals week. Same as all the other ones in terms of closed notes, closed books, and be given a equation sheet. The material covered is everything since 9.11.2, which is pipe networks, external flows, and open channel flows. And it turns out that the questions are picked also from those three topical areas. First one is pipe network, the second one is external flow, and the third one is open channel flows. In terms of the materials you need, you'll be given the equation sheet that comes from this, but as we go through this, the energy equation, as you know, is Bernoulli's equation written between upstream and downstream. It has to be written between upstream and downstream because there are loss terms in the system and gain terms in the system which depend on a sign convention. On the left hand side, upstream is the pump head, which is always positive for a pump and negative for a turbine. And on the downstream side, there are major losses and minor losses. Minor losses are always assumed to be turbulent and given by a loss factor, and major losses are for losses in pipes, which can be turbulent or laminar, depending on the Mooney chart, and scale with length over diameter ratios, and a friction factor, which has to be determined from the Moody chart. And all of them are affected by the mean velocities in the pipe. And so, depending on how you write the equation, this term here might be part of it, and this term might be part of it also, in terms of solving this equation. The pump head is given by the power divided by the mass rate and acceleration due to gravity, which is the same as the volumetric flow rate times density. Together those are kilograms per second, and allow you to calculate power. I guess if you rearrange the equations in terms of upstream and downstream pressure heads, then that constitutes typically the head loss across the system between upstream and downstream if you draw it between two big containers. For pipe flow, we know how to use the Moody charts. They're split by laminar and turbulent flow. They split about a Reynolds number of about 2000. In laminar flow, the friction factor is a inverse function of Reynolds number. In turbulent flow, the friction factor is only a function of relative roughness and not Reynolds number. And so that's important to realize, because when you use that maybe to calculate velocities, you end up with a v squared term for the turbulent flows, which you have to square root to get the velocity, and you end up with a v term for laminar flow, which you don't need to square root. Three types of problems. The easiest ones are class 1 problems, where you're given the velocity, and so immediately you can calculate the Reynolds number and go through the sequence of calculating friction factor, confirming the velocity, and going through this loop. Class 2 and Class 3 problems, which you don't have this time, require that you make some assumptions and iterate. You don't have a velocity, so you have to maybe assume a friction factor, determine a velocity from that, calculate a head loss, and then cycle back to see if for that revised Reynolds number that you have from the revised velocity, the friction factor actually holds. And so you have to iterate your way through the system. You do have a pipe network question, as is suggested. Pipe networks, if they're non-circular cross-section, you can define it in terms of the hydraulic diameter as the characteristic dimension that goes into Reynolds number. Pipe networks come in two flavors. They come as parallel networks, where the sum of the flow rates have to be equal to the total flow. And as a result of that, the head drop between upstream and downstream in each of the legs has to be equivalent. For series flows, if you draw a gate across this at any location, the flow across this gate has to be the same as this gate. So the flow rate in pipe 1 and pipe 2 and pipe 3 have to be the same. And if that's the case, then the head losses are now summed to give the total head losses over the system. So they differ somewhat. For branch networks, you need to realize that since this pressure is the same in both pipes and the ending pressures is different but the same in each of those pipes, then the head losses in these two segments have to be the same. So you end up writing two equations and solving for this value of head at this location as being the same magnitude for both of these exit networks. Okay? Okay, I think that's good. For external flows, I didn't talk about external flows. There is an external flow question, so you do need to know external flows. The drag coefficient acting on something, which allows us to get the force acting on something, is defined very much like a Moody chart. There's a break between laminar and turbulent flow about a Reynolds number of 2000. Reynolds numbers are also defined in terms of a velocity, density of the fluid, and a characteristic dimension, typically, say, the diameter of a cylinder or a sphere. Really, the drag coefficient allows us to calculate from this Euler number. The drag coefficient or lift coefficient is an Euler number, and it allows us to calculate a force that's applied on the structure as a function of density, velocity squared, and area. So the force and the area divided by each other are basically a pressure. So this is pressure rho v squared, which is the Euler number which we have on this chart. So if you have a coefficient of drag, then you're able to calculate the force that acts on a structure if you know the fluid density, the velocity of which it's moving, and also an area on the system. This would typically be the planiform area to calculate. Again, as in the Moody charts, the coefficient of drag in the laminar regime is a function of Reynolds number, and in the turbulent regime is not a function of Reynolds number. And that means that when you calculate the velocities from this, just as in the velocities from Moody charts, if it's turbulent, you usually have a v squared term, which you square root, and if it's laminar, you end up with a v term, a velocity term, which you don't have to square root. Okay. The third question is on opal channel flows. Opal channel flows, we define behavior in terms of flow being driven by gravity. So the gradient of a drop along the length of flow is given by a change in depth over length, or a gradient over the length of the flow. We define a hydraulic radius, which is the area of flow divided by the perimeter. And so this particular case, the area of flow is just width times height, and the perimeter of flow is the width plus 2 times the depth of flow, and the Reynolds number is defined in terms of the hydraulic radius. For uniform flows, we can use the Chezy formula, which is for SI units, this is 1. This is the Manning coefficient, which is really a roughness coefficient. The hydraulic radius raised to the power 2 over 3 as defined here, and the slope of the channel, which is the drop per unit length. So this is just the drop per unit length of the channel. This is the average velocity, which is assumed constant everywhere across the section. So if you want the volumetric flow rate, you just multiply the average velocity by an area, and that gives you a volumetric flow rate Q. And so that's the flow rate question. Actually, that is the question. And for gradually varying flows, these are uniform flows. And for gradually varying flows, we end up with this case where we can have 2 regimes because we have a free surface. It can take this form upstream. So since we have to have the same volumetric flow as we go from upstream to downstream, then upstream, since it's a large cross-sectional flow area, this flow is at very slow velocity. And because of a small flow area, this has to be at large flow velocity. So we can have a fast flow that's deep, a slow flow that's deep, or a fast flow that's shallow. And so we can have 2 different regimes because we have this free parameter, which is the depth of flow, which is we don't really have control over. So we can write a specific energy diagram that defines both of these. These downstream flows and upstream flows represent subcritical and supercritical flows, with the boundary between them being at the critical point, which is a Froude number of 1, and the Froude number is just the ratio of the velocity of flow divided by the velocity of a wave traveling in that flow. And the significance of this is that this is equal to 1 where it's a critical flow, which means that if you drop a pebble in this, the waves that come from this won't actually go upstream. They'll just stay at where you drop the pebble, so no information travels upstream, as opposed to a subcritical flow where if you drop a pebble, it will travel upstream. So no information here. And so these define the break between these different flows. If you draw this diagram, these are the depths upstream and downstream. The minimum energy in the system occurs at this particular nose, so you can start doing some manipulations related to that. But actually, having said that, that's not going to be the focus of your review, I don't think. Okay? So hopefully that'll set you up. Happy hunting on the class. It's been a pleasure having you in class. Good luck on this, and have a great break. Perhaps see you in some other classes later on in your careers. Thanks. Bye-bye.